So Jakob Kilian currently works at the Cologne International School of Design, investigating the interplay between AI and design. He's going to tell us how to exploit brain plasticity to haptically explore the depth of surrounding environments. The talk will give a brief overview of the study and design of the unfolding space glove, enabling blind people to explore the depth of their surrounding. Give it up for Jakob.
Thank you for the nice introduction. First of all, I want to introduce you to Ben. Ben is wearing a device that displays the environment as vibration patterns on the back of his hand. He actually has a different name in reality. He's not Ben. And he participated in my empirical study, in which I tried to find out how well this device can be used to master a specific obstacle course, like the one you can see here in the video. Ben actually is blind with some residual vision, but like all participants, he got blindfolded to ensure absolutely no information reaches him to fulfill this task. Anyhow, Ben seems to have no big trouble getting through the course, and that is because he learned how to interpret the vibration patterns in a visual way. Studies have shown that people who wear similar devices use their visual cortex to interpret this data. So this process is actually just possible due to the so-called neuroplasticity of the brain, which I will come to in a few moments. Hi everyone, my name is Jacob. I'm from Cologne, first of all, and I don't want to talk too much about my background. That's not why we're here today. But it might be interesting for you to know that I didn't have any IT training, actually. I'm not a good programmer. I actually studied design, and I also work in that field. So very often I'd be the nerd among the people that are around me because I'm into techie stuff and many are not. Funny thing, however, is that depending on the perspective, I might also be the nerd in this room here because of my lack of knowledge, in tech and my affinity with design. But I think that's fine, and we'll find a good way of exchanging ideas today. I am constantly searching, and I'm in love with the idea of intersubjective methodological research, which makes me a searcher and a researcher at the same time. And finally, I love to tackle problems. I love to repair, and I love to make things. And in the next 30 minutes, I will show you one thing that I made that all started with this picture of me in the right about 5 years ago. And the end of the project actually was this, and this will be the span of the talk now. The unfolding space glove, which I will talk about, is a wearable for visually impaired people, translating 3D vision into haptic stimuli. The talk will cover 4 topics. First of all, I will spend much time on explaining the theoretical background of the project, and then the glove itself. And in the end, I will give you some insights into the study I conducted and how you can read the results and some findings and an outlook. So let's start with the theory right away. And to understand how we perceive the world around us, we first have to differentiate between the concepts of sensation on one hand and perception on the other hand. Sensation can be described using these well-known symbols representing our sensory modalities, our receptors, so to say. For example, the ear for hearing, the eyes for seeing, and so on. And for sure, there's more than these 5 classical ones, but we'll stick to these for now for sake of simplicity. These receptors now pick up so-called sensory stimuli of the physical world around us, sensations. That is, specific properties about the world, such as the brightness and the color of light rays reflected or emitted by objects in space around us. They translate these into electrical signals. Nothing more than that. And they send them to the brain. And now these days we are very good in observing these signals. Studying them helps us to diagnose and to treat possible disorders of our nervous system and gives us a great insight into how our brain works, at least to some stage. We can even build artificial perceptors by imitating them, for example, the widespread cochlear implant for people with hearing loss. What it does not explain, however, is the somewhat philosophical question of how we end up with having meaningful ideas based on these signals, because until now it's just electrical signals, right? So in other words, why do we perceive blue as being blue? And why do we perceive a cat as being a cat or a Winkelkatze? This is all done by our perception, and this is happening in the brain, which organizes and interprets the information and ultimately gives us our conscious experience of the world. Now, for a very long time, it was assumed that there is a specific brain area, and this is very simple, of course. We don't have more time for that now. A specific brain area for each modality that we have. So, for example, the sensory perceptor, the eye, was connected in an unchangeable way to the visual cortex. This would explain why information arriving in the visual cortex would be perceived visually and not, for example, auditively, just because it arrives in that region of the brain. So the region of the brain somehow defines the quality of the data that comes in. Now, if one of the receptors were to fail, for example, you say you lost your sight due to an accident, you would have no visual perception at all because you would have no way to transfer visual information to the actual visual cortex because there's just one connection between the eye and the visual cortex, and this is not available anymore, right? And these traditional theories, as we will call them for now, have a number of explanatory problems, explanatory gaps they're also called, and we'll have a closer look into one observation, one more recent observation of the brain that it fails to explain. To illustrate these observations, take this blue area in the brain, and again, this is very simple, of course, and think of it as being the language center. Now, if there's any damage to that part of the brain, for example, after a stroke, we now know that the brain can reorganize itself, and even in adulthood, relearn the lost skills in another part of the brain. The skills won't always be fully restored, of course, but in general, it's possible. So this movement of the blue dot here, moving from the damage to another region of the brain, is called neuroplasticity. It is the ability of the nervous system or brain to adapt to changes in the environment by reorganizing neural connections. Now, modern approaches generally take this into account, and again, we can't go into detail here, but in essence, they say that sensory information arriving in the brain, shown here with a white line, does not yet have a specific quality. Instead, the brain examines, and now stay with me because this is getting a bit tricky, the brain examines the sensory stimuli for the characteristics of change due to bodily activity. That means that if you move your eyes, and some piece of that incoming information, of that highway, this data stream of information from all your sensory perceptors, the ear, the eye, and everything, if some of this information changes in relation to that very movement you just did, you can be sure that this part of the information must be of visual nature. And that is why you can actually put visual quality to it, visual qualia, how it's called also. That's actually the reason why you can pick out the visual quality and see in the end. This may be difficult to understand in detail, but it can be summarized by saying that it requires a body and motor action to perceive. And this is why these theories are often called enactivism or embodied cognition in cognitive science. Now let's try the thought experiment again. Let's say the eye has a dysfunction and no longer receives stimuli. You can't see because there is no information. And here's the clue. We are now simply feeding the information with visual quality, so images, pictures, into the tactile sense. The brain now learns to interpret this information as being visual because of the just discussed associated movements and characteristics. And we can now not only use it for everyday tasks, but also develop a visual-like experience with it. Studies have shown this. This concept has a name, a long history of research, and yet it's not widely used or widespread. Sensory substitution means that if one sensory modality is missing, the brain is able to receive and process that missing information by means of another modality, another receptor, sorry. Now looking back on our graph, one last time, there's one thing we need to do to make this happen, because we cannot feel visual images, we cannot feel visual data. So we need a translation device, a device that puts the visual information into our tactile sense, kind of. And that little arrow with the circle here is such a translational device. It's a sensory substitution device, in short also SSD. And that's what actually my project is all about. I built a sensory substitution device. The unfolding space glove is such a device. So in the next session, I'm going to talk about the device itself, the glove. Where does it come from? How did I build it? Let's just dive into that. In 2018, I started to do research on navigation aid systems that use spatial information, 3D information, from a 3D camera. Because back in the time, sensory substitution projects, in science mainly, used standard cameras only, so grayscale or color cameras. That seemed outdated to me, and I saw potential, so I started in researching that during my bachelor thesis. So I experimented with different forms of application. So in the beginning, I wasn't sure that it's vibrations only. I used different means as well. But I pretty quickly settled on the back of the hand as, and vibration as the medium, as the concept. Basically, this rough prototype that you can see here emerged within just a few days. But back in time, as you can maybe think, it was a bit cumbersome and clumsy because it was difficult to put it on and off to all the taping. And also it was very slow, so you couldn't really feel the outcome, but it was a starting point. Then still 2018, a few weeks later, this functional prototype was the end of my bachelor thesis. All the components, including a laptop, were now in the backpack. It was still bulky and impractical. It was heavy. You needed to attach a lot of cable to make it work. And a problem with this prototype, and this is just another close-up shot of the very same prototype, was its high latency. I probably do not have to tell you what latency is, but in this case I mean the delay between your physical movement, the movement of your hand, for example, and the feedback that you can receive as vibrations. And as we learned just in the first chapter, this relation between movement and feedback is key in learning, so it can't be delayed. It wouldn't work well. So I continued to develop the device further. So here you can see an intermediate version of 2019 that does not need any backpack anymore. We have a small armband that you use for running, where I have a Raspberry Pi instead of a computer, and a battery pack. So it was easier to put on and off. It wasn't that heavy. And I also did, in the same time, many improvements on the software side. So now we're in 2020. So software, you can't show that easily, but I also tried to streamline the hardware more. So now we just have this one computing unit consisting of a 3D printed housing, a slimmed down Raspberry Pi, and a battery pack again. And now it was only a single cable connecting the two things. Still, the boot up time was too high, and I got new problems introduced by using the one cable. So a lot of work to do, which I then finished in 2021 with the final prototype that I also will present in a few minutes. I was able to draw on a small grant for professional advice and also for purchase of components. So maybe at that point, many thanks to all the people that helped with the project, that supported me, partly in their jobs, partly in their free time. Some of them are here in the room. Thanks a lot for your help. So now all the components are on the glove itself. We have a carrier board, the computer, the motors, everything on the glove, and we now just have a USB-C cable for power supply. So you plug that in, and the power bank still has to reside on the upper arm. Then you need about 10 seconds to boot the system, and you're ready to go. The biggest difference, again, to previous models is under the hood. It's the performance. The latency between input and output is now less than 50 milliseconds, which is no longer noticeable in practice because vibrations also have some latency. And then of the 50 milliseconds, 90% is due to the camera technology involved, so you can't go any further here. You would need different technology. The exchangeable units, one you can see here in the picture, from top to bottom have an IDC socket, which is the connection between the unit and the glove. So here the voltage to the motors flows. And the second point is the time-of-flight camera, in short, TOF camera. I spoke about that again. So this is a 3D camera that actually determines the distance of each pixel by measuring the time that a light impulse needs to travel from the camera to the object and back. I needed a computer, which in this case is a Raspberry Pi computing module, Compute Module 4. This gets very hot, actually, if you do the research in August with 30 degrees. So I needed a heatsink and active cooling on top. And finally, the most challenging part, for me at least, was the custom circuit board that carries all the components. So the compute module on one hand, and also the drivers for the vibration motors, because you need specific drivers. And you can see those drivers here on the board. And also the board was built under highly professional conditions, as you can see in the upper right picture, again, with the help of friends who know how to do this process. Of course, the whole project is open source. You might have guessed it already. So like the rest of it, this is the open hardware part, of course. You can find all the exports, renderings, and schematics online in the hardware repository. There's 2 repositories. And of course, you find also the keycard files if you want to work with that. Then the building of the glove took like many steps. First of all, you need to select the textiles. You need to develop a robust construction of how to put the cables, how to do the soldering points so that they don't break. If you put on and off the glove, people don't really, they aren't really careful with putting it on and off, so you have to think that first. And all this tinkering is also documented, so there's a step-by-step building instruction of the glove that you can find on GitHub. So also, if you don't want to build this glove, but have something similar in mind, this would be maybe a good resource to start. Then, last but not least, challenging for me at least, the code. It is written in C++ because of the camera library. And if that wasn't complex enough for me, I also had to integrate multi-threading over time, again with help of friends. And I built up a cross-compile environment to be able to iterate and develop quickly. If you're not a good coder, iteration is key. You can also find, of course, all the software parts on the main repository with some documentation as well. Also the source code files, of course. I used a lot of libraries and locking things. Probably you could do these things more efficient, but my part of the processing actually just takes 3 milliseconds, so there's not much to gain here. So, time for a short summary. The final prototype is a spatio-visual to haptic sensory substitution device. That's a long, complicated sentence, so what I generally do is I take depth information and make it haptically tangible, haptically feelable. It is also a navigation aid system with low complexity and low entry barriers. Why low complexity? I only have 3x3 motors, so you can actually just see that there is an object. You couldn't see which object is there or which specific properties it has. However, it allows you to learn the system more quickly, so you could make it more complex later on when you learned it, for example. The final prototype has some unique properties that I worked for and that also could be proven to some part in the study. First of all, I am using a 3D ToF camera, already said that, so instead of grayscale cameras that most studies use to that point, and that is just because 3D images are more accessible than standard grayscale images, because you want to have the location of objects in the room. If you have a grayscale image, you would have to analyze light and shadow, perspective, parallax, all these things to actually extract the location data. You just skip that by using a 3D camera, which hasn't been there, of course, when they started to do sensory substitution studies. Now, the second point is using the back of the hand as in and output offers a very high degree of possible interactions with the data. So you can actually rotate your hand and move your hand in 3 axes. So as we've learned, interaction is key to the learning process, so that makes the first steps easier. Also important for the learning process is, of course, that the feedback is continuous and that it has a low latency. We spoke about that. And the device has low costs on top. So that is mainly because I use mass-produced and non-critical technology, so you can actually put it on and also put it off if you don't like it. There's no surgery needed or anything like that. The components for the prototype would now be around $500. I started the project 5 years ago with technology that is available here. Today, you could build it for probably for about $100 without the ToF camera. And last but not least, it is also variable already. I mean, with that you can use it outside of the lab. Many projects have to stay in the lab, have to stay in a specific system. So here we can go out in the bright sunlight on the street with an 8-hour battery charge. Right, and next is you just put the unit onto the glove. I already have it here on the glove, and you put on the glove. Then you have this little strap where you can place the battery. You place the battery by just turning it once, plug in the cable, and then the system boots up. As I said, it's about 10 seconds, so in a few seconds I will be ready to go already. And I can show you now the data in a few more seconds when also Wi-Fi is set up. Hey. Okay, I can't click here. All right, so now you see what I feel actually. Doesn't work again, that's so sad. Okay, you at least see the screenshot, you saw it for 1 second. I can go back to the presentation where we have one picture showing an exemplary okay, all right. An exemplary picture. So on the left side, you see the motor values, which range from 0 to 255. Blue actually is very close. Purple is even closer. Green is about 1 meter, and then after 3 meters, there's a cutoff. So all the black things we ignore. You can also. This is just a setting. You can set it to off outdoor mode or to indoor mode, and on the left, like this app is also there for the study, of course, to see what the participants saw, and also for getting some monitoring data, like how warm the glove gets. Still doesn't work. Okay, let's go back. That's actually the depth image, and as I said, on the left side, you see the motor values. Okay, I will give you now a short overview about the study I conducted. So first of all, I had 6 blind and 8 sighted, but blindfolded subjects. The central idea here is that by including the sighted subjects, it is possible to compare how quickly devices can be learned if you have to learn both devices from scratch. I had a complex study design which also used mixed models to actually make use of that combination. I had a controlled test environment, the obstacle course. You can see in the upper right image the numbering system on the ground to place the obstacles in a quick manner. And on the bottom you can see one course set up. I used qualitative and quantitative assessments. So first of all, I had, of course, the time you need to solve one course and the resulting collisions. And secondly, I had questionnaires and interviews collecting the feelings and the needs and thoughts of the users, especially, of course, from the blind users. Well, then the subjects had to do some paperwork in the beginning of the study, and then they started to explore the room with the glove, so they could, in the training process, ask all sorts of questions. I had some semi-structured training program where they could point on objects, then grab for them, pass them. All of that was basically to learn the very difficult part, to understand the relations between the felt patterns and the reality, so kind of the adjustment in the beginning. And then in the test runs, so this is videos of the test runs, they were on their own, trying to solve a predefined pseudo-randomized set of courses. And as you can see, they did it with both devices. And they completed all course layouts twice without realizing it. So I had one version, which is the regular version on the left, for example, and then on the right side, the same course, but mirrored. That is not just a clever statistical move that someone told me again, but also we have now footage of the very same course actually done with the two devices by the same person at the same stage of training. So what you can see here is that the cane is faster, always. And you can also see that the glove works. You can see that the wayfinding actually is nearly perfect, so even better with the cane sometimes. So kind of taking the optimal path, but slower. And this is kind of the main finding of the study as well, that I actually expected before doing the study. So getting into the findings and outlooks, the first and main finding is that the sighted group, which had to learn both devices, over a duration of the study itself, so 2 hours of wear time with the cane and the glove. Over that time, the cane is faster and causes fewer contacts. So what does that mean? Whole project is failed, or what's the answer here? So no, that's not the case. That's science, actually. I want to tell you why this study still has some very interesting outcomes. First of all, I expected this result, as I said, before the study. But what I didn't expect, actually, is that all subjects could solve all the courses. So in total, they did, over 2 months, they did 800 runs, and none of them failed. So that is a proof, actually, that subjects could learn to navigate through this specific course by using the device. Secondly, I often experienced a very good performance already some minutes after the first tutorial with the device. So just a note, in many studies about SSDs, they just let subjects use the device for dozens of hours, in one case even 180 hours. We had just 2 hours of testing, of training before we tested. So just look at Ben again. Ben is here walking 3 minutes after he got the device on first, and he kind of chooses the optimal path already. Of course he's slow, you can clearly see that, but no 880 hours needed here to get started. The third point is, there are many examples of highly efficient wayfinding. I already told that. So that means that even if you're slow, you kind of take the optimal path. And some of the users also reported, no, most of the users reported deep sensory integration, meaning they said things like, I don't have to concentrate on the vibration patterns anymore, I just know that there's an object and I walk around, because that's what you do. And also, the last point, I already said this as well, there was a positive user experience. So people had actually fun to learn the device, and it was an interesting new feel of the world to have it with vibration patterns. All these things are summed up in numbers and graphs in a scientific paper that appeared in 2022. Again, open access. And I'm very glad, actually, that it has been quoted for a few times, just because my efforts always were that this project isn't there for just a few pretty pictures and then ends up in a drawer, but that it would be found on the internet maybe, and people take it, reuse it, and put it in their project as well. That already seems to work. However, to actually get proof for some of the derivations that I did here, you would need more research. It would be interesting to see how people perform after 10 hours of training, after 20 hours maybe. But for all that, you would need funding, you would need institutions to work with, and that is a bit difficult with such a niche topic. So that would be kind of the summary, the outlook of the project. But for now, I'd like to thank you for your attention. Sorry for the messed up live demo. It's always like that, I guess. If you have any questions, go to my website or just ask your questions now. I will be around for a while, and if you want to try out the glove, we can arrange a meeting probably in the next days to test it.
So you mentioned that there's a deep sensory integration, and also that you assume that this is in the visual cortex. So for the formerly seeing people that are now blind, did they have some sort of visual feedback in terms of colors or feelings, or how did you come to this particular conclusion?
So you mean how they described the actual feeling they had? So the point of this deep sensory integration leads or points a bit to that direction, because they said they don't have to kind of interpret what they feel, but they kind of know that there is an object. And when you ask them, like, do you see it, then they wouldn't reply like that. And I didn't ask it in the study because it would be a suggestive question, of course. But afterwards, they describe it a bit differently, because also the information is so low complex, probably. I said that because there are studies about sensory substitution devices that they take a similar approach, and they could actually prove that in the MRI picture, the visual cortex get active when you train a lot with these devices.
So given from your findings, would you say that a seeing person does perceive this different than a non-seeing person?
Yes.
Okay.
Yeah, blind people and also visually impaired people have an easier time learning it, probably.
Mic 3.
Thank you for your excellently delivered speech and your talk. Very clear. My question is about placing the PCB on the knuckles of the hand. I see why you would do that, because the 3D camera must be there. But isn't it very fragile there, and fragile for bumping into things?
Yeah, probably. I mean, you would have to build it. It's not a product that you can use on the streets. Actually, it's a prototype. I said you can use it there because it's maybe a good reason to test it on the streets. But it's not. Also, for many other reasons, not at all a replacement for the cane, for example, which is very versatile and reliable. So this is just a prototype, and you would need to make protection for destroying it, of course. I chose the region because the sensor and the actors, in my opinion, have to be very close to each other, so that the feedback loop is kind of set up. And the position of the hand, having it like that, is a pretty natural one. So many people suggest doing it on the inner hand, then you would walk around like that, which is a lot more effort, I would say.
Cool. There is a question from the internet.
I have 3 actually, but the first one is, are you familiar with Professor Thomas Metzinger? That there seems to be similar value of research.
I didn't understand the name correctly, but I think I heard it.
Thomas Metzinger.
I'm bad with names. Probably yes. I mean, I basically read all the sensory substitution device studies, so probably yes.
Go ahead. The next one. Okay, let's go with 3.
Hello, hi. So from what you said about further research and the need for funding, I I gather you don't develop it currently as a commercial product at the moment. My question is, have you tried seeking this venue? Have you tried looking for funding for making it into a commercial product? And what were the responses?
Not really, because I wouldn't consider it as being a commercial product or a navigation aid system with all the functions that you would need in such a device. To me, that is a research project that looks into how you can interpret 3D data. I already said it, but for example, it's a very limited scope of information that you get. For example, objects on the ground are not included yet. Only if they have a specific height, then they would be in the picture. So this is just a tool to research into how you can integrate 3D vision with vibrations, actually. Tactics.
Me? Yeah. Okay, yeah, sorry. Thank you for the good speech. And my question is, have you experimented with different sensors, radars, for example, and why did you choose your specific time-of-flight sensor in the end? Yeah.
In the beginning of the project, there haven't been that many tough sensors, for example. There's very cheap ones out now. At least I didn't find them, and I wanted to be as flexible as possible. So I wanted to build a platform where you can also do different things with. So we have now Raspberry Pi, which has a very low CPU load, so you could now, for example, also do object recognition tasks and other things on the Raspberry Pi. If you would go for an MCU with a smaller TAF sensor, you couldn't do that, for example.
Yeah, okay, thanks.
Nice. Mech 3?
I just have 2 questions. The first one, as I can see, like from the arm, for example, if you have like a hole in the ground, then it will be really hard to detect the hole somehow, then the blind people will fall down. The second question is, like, why you didn't design your own PCB somehow, and then you can make it to the SMD, so you can create your own mini computer specifically for these tasks, because then that will save the power consumptions of the battery.
Yeah. So to the first question, I needed to reduce the things that I can research on. So I researched on, first of all, getting the 3D data, how can we interpret it, and how well would that work in a very limited way of obstacle course, these boxes. So you would need to integrate that. I think it's possible by scanning the floor to differences and these kind of things. And there's also the possibility of mixing the cane with such a device. So it's in the left hand, the cane will be in the right hand for most people, and you can switch it. And the second question is kind of the answer of before. Of course, if I could do it, if I would have the ability, I could build such a PCB. But for now, it's a prototype. So with this one, I can also just switch the camera if it gets broken, and it did break in the study. So I'm very glad that it's kind of modular, and that I can put things on or off if I want to go in a different direction, because I didn't want to put all the possible developments in already by choosing a PCB, a specific PCB.
Okay, thanks.
Maybe one last question from Chu.
Hi, nice project. I saw you have 9 different vibration devices on the glove.
Yeah.
Right?
Motors, yeah.
Yeah. How did you go about mapping the time of flight information to vibration?
It's actually a pretty simple and algorithmic thing. I do a histogram and search for the closest object that exceeds some threshold, because you have some grain and some noise that you want to filter out, and then it's basically a pretty quick task, yeah.
Okay, thanks.
Okay, any other question just after the talk? Thank you.